About central force. So before reading about this concept, I want to just talk about this in a regular distance. By understanding about the regular distance. So let's suppose this is a point A and this is a point B. So if someone asks what is the distance between point A to point B, you will just give from here to here. So this is a normal distance. But I want to make you clear what about the radial distance. So if someone asks radial distance, so radial distance, let's suppose this is A dash and this is B dash. So if someone asks the radial distance, it is from the center point to the another body's center point. So this distance, this is the r distance, this is the radial distance. Now let's move on to the central force. So let's suppose this is a particle point at point P and this is a particle at point O. Central force actually acts along the line joining the two interacting particles. So this is the line, this is the radial distance as mentioned. So central force acts along this line. This is the force. And you know what? Another key point, the magnitude of the force, the magnitude of the central force is equal to the radial distance from the point P to the point R. It is a particle and it is denoted by this because magnitude of the force is dependent upon this, so we keep this as a function kind of thing. Now let's move on to another thing, that is it may be repulsive or it may be attractive. So one repulsive force example, we can write. So before that, it may be repulsive or it may attract or it may repel. So we can write this as it may be repulsive. If repulsive, it's negative. If positive, it means the attractive force. And it may be written as this. And then let's move on to the examples. Talking about attractive force, gravitational force, of course, a gravitational force attracts a body. And repulsive force, electrostatic force, it may repel sometimes, most of the times. And another example is the spring force. It also. So now talking about the conservative, its key points. It is a central force is a conservative force. It means the force is the negative gradient of any scalar function. So it is a nebula. So let's not move on to this. Next key point is the angular momentum is conserved, the angular momentum conservation. So before that, I assume that we all know what is torque. So torque is equal to mass into the radial distance, sorry, the radius square. And we know the angle linear, sorry, before that we need to know about linear momentum. So linear momentum is defined by this, denoted by this, and its formula is mass into the velocity. So we know the angular momentum. Now this is angular momentum. So angular momentum means the multiplication of linear momentum to the radius. It is a distance, sorry. And mv means the formula of linear momentum. And next, moving on to this, the relation between torque and the linear angular momentum relation is something like this. So tau is equals to, it is called as tau, change in linear momentum upon change in time. So if in the central force, now the main point is in central force the torque is equal to 0. So this is something like condition of the central force. It is a key property of central force. So if tau is equal to 0, then we know the relation between tau and the linear momentum, angular momentum, sorry. So 0 is equal to this. Now if this will goes down to multiplication, and that means dl is equals to 0. So there is no change in the angular momentum. So angular momentum is conserved. So this is something we need to know about the central force. In this, angular momentum is conserved. So these are something that we learned about today. On to the next part, that is two body problem and reduce mass. So before that, consider two bodies. So this body and this body of masses m1 and m2 located at position vectors r1 vector and r2 vector respectively from the origin O. So this is the mass 1 and mass 2. So these are located this far from the origin. So it is r from the origin. The position vector is r1 vector and r2 vector. So next, the force between two bodies is directing along the direction of r vector. So here, so I need to write this as r vector. Now let the force exerted by m2 on m1 is f vector 1 2. So f12 is the force that is exerted by m2 on m1. Now next, the force exerted by m1 on m2 is f21. So this one, from the Newton's third law of motion, we know that Newton's third law of motion, to every action there is equal but opposite reaction. So like this, we can write the force that is equal but it is opposite in reaction, therefore it is equal and it is the central force. Now, so now using second law of motion, so Newton's second law of motion for m1, so from the mass 1 we need to calculate the force. So Newton's second law of motion talks about the force, mass into acceleration, product of mass and the acceleration. So this is the mass and this is the acceleration. As you know, this is the formula. We just converted this. And so yeah, now this is the force F2, and this force is also denoted by this, because we have in the equation 1 we have equal this value to this, as we got the value that to know that this F12 is equal to this. So now we need to do this a bit little one, this. Now we will move on to this. So this m1 goes to this, and we will be writing this as a central force. So this will be our equation second. Now same for the m1 so for m2 using doing the same thing, but as we know for 2-1, so for the force m2 we have for the mass m2 we have the force this 2-1. So in the equation first we got to know that F12 is equal to negative of F21. So for that now we need to change a bit formula, so it will be equal to negative 2-1. So now it will be the central force is the repulsive force. So now a little bit more. This, oh sorry, I need to do this because it is the radial distance we are taking this. So d square is equal to negative of 1 by mass m2 to the central force. So will be this will be our equation third. Now next, so we got this two equations. Now what we will be doing is we will be subtracting equation 2 from equation 3, then we will get this one. This is the final result after subtracting this. So equation 1 we have this and which is equal to this, because we are subtracting from m1, so it will be like this. Now furthermore solving it, so this will be minus r vector 1. We have that dt square is a common, so no need to take the LCM. Now what we're gonna do for this is we will be taking negative sign as a common, and m2 plus m1, and then even this and this is a common factor, so fr and this. So yeah, this will be our equation fourth. Now before that we know the vector law. What vector law says, so what triangle vector law says is r vector, this vector, is equal to r2 minus r1. So now using vector triangle triangle VCTOR vector law of ADDITION addition, we get r vector is equal to r2 minus r1. So in this equation we could replace this with equation this r. So after replacing this, d square r dt square is equals to negative of this 1 by m2 plus m1, and now this. So now again let's say this, let's take this. So let's take this as a mu. So mu before that let's take this as a mu 1 upon mu. So 1 by m2 plus 1 by m1 is equal to mu. So what will be the value of, let's suppose this is a mu, okay, let's take this aside, and this will be like this, equal to negative mu f this one. So it will be like this. Now finally mu r is equal to dt square is equals to negative central force. So this is the final derived answer. This is the final derived equation. Now for this mu is our reduced mass. So mu is equal to, after doing everything, m2 m1. So this mu is the reduced mass, and what we can say is a two body problem can be reduced into a single body problem under central force by replacing the mass of a body with mu is equal to m1 into m2 upon m2 plus m1, keeping the position of other bodies as fixed. So this is the reduced mass, and in this REDUCD, and this is all about the central force. I hope that you will understand everything about this. It is not that tough. This is what we did. Thank you. Please watch, comment, do subscribe, and give us feedback.